Hello, my name's Adrian or Alice, or I don't really mind what people refer to me as, but I kind of like Alice Fox. It's nice, it's a pretty name. And we're going to do a little geometry lecture, and I'm going to try and take a more formal approach and really show the viewer what is happening here, what this is all about. So here we have complex broken symmetry. This is broken symmetry, and it utilizes 4 to 5 axis points or vanishing points, and it's different than susy or supersymmetry, right? Right? Okay. So susy, I like that word, by the way, susy. It's that supersymmetry sounds so serious. It's like a big deal. Like, fuck, supersymmetry. It's like intimidating. But susy is just kind of cute and manageable. You know, it's just susy. So susy is broken symmetry. If I had multiple sets of broken symmetry, right? Or I had multiple quantum states or interiors of atoms. Susy is the symmetry, like the quantized symmetry between all of the broken symmetries. Okay? So that's what susy is conceptually. That's really what it is, okay? And it's like that because it correlates pheromones with that of massless bosons and mass bosons. And when you have like massless bosons, you start getting into inverse reversibilities, like of quantum states. It's like starts getting into the field of, like, it starts getting into quantum field theory and what isn't understood about correlating quantum electrodynamics with that of the weak force and radiation, etc. Okay, so this is of a quanta, you know, like a system, not multiple systems, which is susy. Okay, so what is happening here is we have an exterior layer, which is the outer vertices or axes, or we'll call them vertices, they're not axes. And then we have a second layer, which is the interior, these lines, this one behind here, okay? And then this is our third interior layer. It's not a complete model. What needs to happen is this third interior layer needs to be further broken. And what I mean by further broken is it needs to be furthermore elongated. It needs to be crushed more, right? It needs to be more of a broken nature. And what that will do is this second interior, these lines in particular, will weave through this structure and unify it more, make it structurally like way more sound. Like the difference between these lines not weaving through it and them weaving through it is like absolutely massive. Like in terms of, if this was scaffolding for a spacecraft, for example, and that scaffolding, by the way, you could run all your optical, electrical wiring through the scaffolding, and you'd have a really, really beautiful distribution of an electrical network. But that's another matter. But it is connected to this. So, and if you think about weather or impact on the scaffolding, impact of any kind, like an asteroid or weather or whatever it may be, each vertice between connection points can be thought of like a tensor, like it has a flexibility, it has an ability to absorb heat, and then the distribution of the symmetry is like the sum of all these tensors that an object comes in, impact happens, and the tensors, the symmetry of the tensors absorb the heat and the impact in a unified manner. It's important. It creates like an equiaxial absorption of impact. And what we have is, it's pouring down rain now, but what we have is a vanishing point here. We have a vanishing point for this, where they all go off in this direction, all the vanishing points. We have another vanishing point coming off this line, another one coming off this line, and then this line here, there's another vanishing point inside of it, right? So you have 4 vanishing points, and then what starts to make it 5th dimensional is the sum of these vanishing points and the angles between them added up as if they were amplitudes, right? And you get an interior vanishing point. And this interior vanishing point is crucial and underpins complex broken symmetry. Okay, that's kind of how this works. Like the interior vanishing point is everything. It's almost, it's what underpins the whole structure. It can't exist without the interior vanishing point. Okay. And then here, this whole entire drawing is what derives this interior geometry. Like, you can't draw this unless you draw this. It's a sphere, obviously, Pythagorean triangle reversed. It's around the other way, okay? This spins in this direction, but it spins in a corkscrew motion. It's called complex spin, and it's when the spin doesn't remain on the surface of the sphere, it slowly spirals in, okay? And that's what's happening. That's why this angle gets shifted like this, and then shifted like this, and then shifted like this, and shifted like this, and like this, and like this, and this, okay? And then this kind of does it the opposite way around. Like, it folds into it, but it folds out of it at the same time. It's hard to explain with English. It's very difficult to explain. We have a vanishing point, this shape here. We have another vanishing point, this shape here. Here's the line for it, you see? There's another line for it. There's always two shapes. It's like a 3D shape, okay? Here's this one. And then there's an off of this one, you get a little complex one that comes up here. It's just like a rectangle kind of shape. You get another one here. So you can see there's a vanishing point here, 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 and then personally what I'm going to do is this whole thing, I'm going to fold it into this, or I'm going to fold this into this, and they're going to meet each other in the same, like in the middle, right? And this, all of this will make the scaffolding for the whole exterior of this. Okay? And it'll quickly get really quite incredible. And you know, that's kind of what this is all about. And it's more than that. Like if you want to use it for particle physics, like if you use it for particle physics, like say the whole thing is a proton, right? The whole thing is a proton. So we put the spin of a proton on it, okay? And then these here, these two triangles, we have like 6 vertices, and the 6 vertices represent the values, the energy values of quarks. And when we spin it, we get a change in vertices, and there's going to be associated with gluon energy exchange, there's going to be a quanta of gluon exchange, and like a quanta of like possible quark arrangements, right? All of the amplitudes of quark arrangements and that of the quanta of gluons is going to start giving us answers for, quantifying quantum electrodynamics with radiation and weak force, because now we have a quanta of massless bosons and their association with mass. You see? Just like how we had Feynman diagrams, or we have Feynman diagrams, eventually we're going to have some kind of other diagrams. I call them Fox diagrams, just for the sake of things, where the diagrams explain, the quanta of gluon energy and that of all possible quark relationships, and you'll have to do it for a neutron as well. So you can't just do the proton, like you have to do the proton and you have to do the neutron, and then the correlation between the two sums is what's going to derive like your equation. Okay? You don't get to just do one, obviously. People should know that. Yeah, it's what it's all about. Yeah, it's very interesting. Okay, bye.